In our previous video, we looked at the population growth, assuming that the population could grow infinitely without any limits. However, in real life, there's often a limit on your population growth. Your population may be limited by living space or food supply, etc. And so what happens in this situation is that we get this upper limit. Our population begins to increase exponentially, but then we reach a point where we can't really have any more in that particular environment. We call that upper limit the carrying capacity. And in our function for population growth with a limit, that numerator is going to represent our carrying capacity, our upper limit of the population. We may then also be asked to find the growth rate, as we were in the previous population problem. Our growth rate, once again, is going to be represented by the variable k. However, this time, notice the negative sign is in there. Because we want this to be a growth and not a decay, we actually need to take the absolute value of that k value, and that will tell us what our population is growing by. A is going to be just a constant that's given to us in the problem. So let's go ahead and take a look at an example of when we have a limit on our population growth. So once again, our first couple of questions involve us just analyzing the equation that we're given. In this case, this equation models the number of fruit flies that are present in a milk bottle after a certain number of days. And so my first question is, what is the carrying capacity? Well, this is going to be the numerator of your fraction. So 230 fruit flies will be our carrying capacity. That will be the upper limit of flies we can have in this population. We won't be able to get more than that. The population should balance out at that point. My next question is, what's the growth rate of the population? Well, this will be my k value, or more specifically, the absolute value of that. So in this case, if I change it to a percent, 37% will be my growth rate. To figure out my population after 5 days, I'm going to need to go ahead and plug 5 in for my time. Now notice, back in the original description of the problem, it did say that t was measured in days. It's important to make sure that those units are consistent. So I've gone ahead and written out my equation with 5 plugged in. Using my calculator to very carefully get that typed in and evaluated, I come up with approximately 23 flies after 5 days. Now in this case, since our population represents a specific number, it would make sense to round to the nearest whole number. In this case, we can't have a fraction of a fly. And for my final question, I'm asked to determine how long will it take for my population to reach 180 flies. Well, to do this, I'm going to set my function equal to 180. Notice t is my variable because I don't know what the time's going to be. This could be solved algebraically. However, I think what I want to do is I actually want to solve this using a graph. So I'm going to get my graphing calculator in just a moment, and I'm going to enter in the two sides of my equation as y1 and y2 and look for an intersection. That intersection will be my answer to this question: how long would it take to reach a population of 180? So let's switch over to our calculators and take a look at finishing this question.